Hi, this is Dr. Kunka Bheemalingappa. I heartily welcome you. Present topic would be proving that NFA and DFA accept the same language. So these are the contents. First, we look at what are these NFA and DFA, and then we are going to look at proving that NFA and DFA accept the same language. We are known the basic difference between NFA and DFA. The basic difference between NFA and DFA is that in NFA, for a given state and input, we will have two or more outgoing transitions. Whereas in DFA, for a given state and input symbol, there will be one and only one outgoing transition. So this is the basic difference between DFA and NFA. For a given regular expression, first we are going to start the construction of epsilon NFA. In one of the previous video, I have discussed how to translate this regular expression to epsilon NFA. And also, we have seen problematically how to convert this epsilon NFA to NFA and then NFA to DFA. We came to know that all this epsilon NFA, NFA and DFA for a given regular expression, all they must accept the same language. Right? So, and you are known the transition functions of this NFA and DFA. First, let me take, that is NFA. NFA is what? Non-deterministic finite automata. NFA is a non-deterministic finite automata. The transition function of this NFA is this. If I let NFA as say M1, if I let this NFA as M1, and you are known, this NFA is a phi tuple, that is a set of states, sigma, transition function, start state, and a set of acceptor final states. These are the states that what we are going to have. Let me use the subscript to differentiate between this NFA and DFA. That is, this is say Q1. Whenever you find this a subscript 1, it means that that is NFA. So the transition function of this NFA, we are known what is the notation that what we are using. That is delta 1 is a transition function. You are known about this phi tuple. Q1 is a set of states, sigma 1 is an input alphabet, delta 1 is a transition function, Q1 is a start state, and A1 is the set of final or accept states. Now, the transition function of this NFA can be defined as follows. That is delta star of Q some state Q1 epsilon is or Q itself. Delta star of Q epsilon is Q, but here we are using the transition function notation as delta 1. Therefore, I can say delta 1 star of Q1 epsilon is Q itself. Whatever the state here you have, that it becomes. Next, delta 1 star of Q on A is equals to delta 1 of QA. In one of the previous video, I have clearly discussed about the difference between delta and delta star. We are going to use this delta star for the current input symbol, for which you have to find the transition function. Right. In a similar fashion, for A belongs to, that is sigma, and X belongs to sigma star, X belongs to sigma star. Just now I have seen for A belongs to sigma, what is this delta 1 star of QA? That is equals to delta 1 of QA, that is being one input symbol. So if you have say delta 1 star of Q some state, that Q belongs to what? This Q1. Q1 is a set of states. Yeah. Delta 1 star of Q XA can be stated as follows. Being this is NFA, you will have more than one outgoing transition. Therefore, you are going to get this union, that is union of R belongs to, what is the notation you are using for NFA? That is delta 1. R belongs to delta 1 star of Q X. R belongs to delta 1 star of Qx, delta 1 of R A. This is the transition function of this NFA. So what is the difference between these two? Here you have A, here you have XA. In the sense here X is epsilon. So if I take this X as epsilon, you are known delta 1 star of Q on epsilon is what? Q itself. In a Q itself. So this can be rewritten as what? This can be, if you want to rewrite this, right, you can write. This can be rewritten as union of R belongs to Q, delta 1 of RA. But you got this Q because of this rule. That is delta 1 star of Q epsilon is, that is Q itself. I think I understood this. Next, moving on to, there is DFA, deterministic finite automata. It is also a phi tuple. I'm going to denote this DFA with a small notation, that is M2. M1 I'm using for NFA, M2 I'm using for DFA. M2 can be, M2 is a phi tuple, that is DFA is a phi tuple, you are known. Phi tuple consists what? A set of states, input alphabet, transition function, and then some start state, and then a set of accept or final states. So I'm using the notation that is M2. Therefore, I can use the subscript, that is 2 for all these symbols that whatever you have in this phi tuple. That is Q sigma delta start state, that is Q2, and this is A2. First, let me give the definition of this DFA, and then we move on to proving that NFA and DFA, they both accept the same language. So I'm using the notation for this DFA is delta 2. So what it says is delta 2 of Q, say some state belongs to this Q2, sigma is equals to what? Q itself. In a similar fashion, now we are going to this look at the transition function for one input symbol and more than one input symbol. Right. So delta, just a second. Yeah. So here also I can use star. Yeah, delta star of Q epsilon is Q itself, and also delta star of Q single input symbol, say A, then it is equals to what? Delta 2 of QA, delta 2 of QA in a similar fashion. For this is for A belongs to sigma. In a similar fashion, we have for some X belongs to sigma star, delta 2 star of say some state, say X, Q, XA is equals to what? Delta 2 of delta 2 star of Q X A. This is the transition function of this DFA. These are the basic definitions of NFA and DFA in terms of the transition function. But mainly we are interested in proving that NFA and DFA, they accept the same language. They accept this, you are known, sigma is the input alphabet. You are known input alphabet is same for both NFA and DFA, right? So I can say here itself I can tell some important points. These are some observations that what we can make. There is, let me end here. In the next slide, I can write. So we are known sigma 1 is the input alphabet of NFA and sigma 2 is the input alphabet of DFA, that is M2. It should be the same for both. Therefore, I can say sigma 1 is equal to sigma 2. That is input alphabet is same for both. And also the start state of NFA, I have taken it as a what? Q1. And the start state of this DFA as that is a Q2. You are known. The start state is going to be the same. In the example right you have seen. The start state, when we have seen conversion of NFA to DFA, we have got the same state that whatever you have as a start state in NFA, you have got the same state as the start state in DFA. So these two are start states in the sense they are also same, that is Q1 is equal to Q2. These are two important observations and this is the most important. Q1 is equal to Q2. And mainly we are interested in proving that NFA and DFA, they both accept the same language. They both accept the same language. So you are known for DFA, I am using delta 2. For NFA, I am using that is delta 1. Just now, right, you have seen the transition functions of both. That is NFA and DFA. In NFA, you are going to find that union. Right? Yeah. So, delta 2 of delta, otherwise say delta 2 star of, say, some state say Q, XA is equals to what? Delta 2 star of QXA is equals to what? If they both accept the same language, accept the same language, you are known. The transition function of this NFA is delta 1. It must be equals to what? Delta 1 star of QXA. If they both accept the same language, then this must be holds good. So, in a similar fashion, delta 2 star of Q A must be equals to what? Delta 1 star of QA. Delta 1 star of QA. With respect to one input symbol, you are known this A belongs to sigma. Yeah. You are known there is no difference between just del and delta star. So I can say delta 2 of QA is delta 1 of QA, I can say. Delta 1 of QA. So these are important observations that you have to remember. That is delta 2 QA is equals to delta 1 of QA. Delta 1 of QA. Yeah. Moving on. With this assumption now. Yeah. You are known delta 2 star of delta is 2 is what? DFA, right? Yeah. Delta 2 star of QXA is equals to delta 1 star of QXA, right? So delta 2 star of QXA is equals to delta 1 star of QXA, And you are known the definition of this NFA. In the first slide I have given delta 1 star of Q1 XA is this. That is M1. Delta 1 star of QXA is equals to union of R belongs to delta 1 star of QX delta 1 of RA. Right? So I can rewrite this formula if they both accept the same language. Yeah. Wait, yeah. Yeah. So this can be rewritten as what? Union of R belongs to delta 1 star of Q X delta 1 of RA. See, on the left side you have delta 2, on the right side you have that is delta 1. That is an important observation you have to make. This can be rewritten as what? Union of, yeah, this is what this. Suppose if it is a delta 2 star of Q just A, in the sense X is epsilon. X is epsilon in the sense, let me change this color. What happens? Union of, let me write here, little for, R belongs to delta 1 star of Q epsilon. You are known delta 1 star of Q epsilon is Q itself. Delta 1 star of Q epsilon is Q itself. Therefore, R belongs to Q, delta 1 of R A. This is the important thing that what you have to remember in proving your theorem. This is going to be very much useful to you. Right? Yeah. If you want, you can give some name, okay, for this. Say, we have taken this. We are known Q1 is equals to Q2. If you want to call this as, say, equation, say, capital A, you can call. And let me call this equation, that is delta 2 star of QA is equals to union of R belongs to Q delta 1 of RA. This is the equation B, right? So they are going to be very much useful. So now moving on, first let us prove that delta 2 star of Q X is equals to delta 1 star of, you are known, delta 2 is the transition function of DFA. Delta 1 is the transition function of NFA. So delta 1 star of Q X. This is what I have to prove if they both accept the same language. So consider the left hand side part. You are known what is there on the left hand side, that is this. Consider delta 2 star of Q X, delta 2 star of QX. Here let, you are known, X belongs to what? Sigma star. Sigma star in the sense what? 0 or more symbols from the alphabet. So if I take the 0 symbols, in the sense that is epsilon. Therefore, let X is equals to epsilon. Let X is equals to epsilon. Then what will happen? This equation can be rewritten as what? That is, this is equals to delta 2 star of Q epsilon. And this delta 2 is a what? Transition function of DFA. For the DFA, I have taken the start state as what? Q2, right? So let me take this as what? Q2. Let me take this as Q2. I think you understood the reason, right? So this is equals to what? And you are known delta 2 star of Q2 on epsilon is what? That is Q itself. Here Q is what? That is a Q2. Delta star of Q epsilon is Q in the sense delta 2 star of Q2 epsilon is equals to what? Q2. There you have Q, here you have that is Q2. That is the only difference. There you have delta, here you have that is delta 2. Right? So this can be rewritten as what? That is Q2. This can be rewritten as what? Q2. And you came to know that Q2 is equals to Q1. That is a start state for NFA and DFA is going to be the same. That is what I have made the conclusion, right? So for that I have given some equation name also. That is A, right? Q1 is equals to Q2 or say Q2 is equals to Q1, right? So what I can do? Yeah. This is equals to Q2 in the sense this can be rewritten as what? This is equals to Q1 itself. And I have used this Q1 as a what? Start state of NFA. And what is the transition function name I have used for NFA? That is delta 1. So I can rewrite this as what? Delta 1 star of Q1 epsilon. We are known that with respect to NFA as well as DFA, delta star of Q epsilon is Q itself. Here, in place of delta, you have delta 1, and in place of Q, you have, there is Q1. And we are known that I have letted this X as epsilon. In the sense, epsilon is equals to X, or say X is equals to epsilon, both are same. Therefore, I can rewrite this. What I can rewrite this? This can be rewritten as what? Delta 1 star of Q1 X. I started deriving with what? Delta 2 star of Q2 X. From that I have got what? Delta 1 star of, see here you can verify, delta 2 star of Q2 X. So from delta 2 star of Q2 X, I have got what? This delta 1 star of Q1 X. Right? So for X belongs to sigma star, you have shown, right, in a similar fashion. We can also prove that delta 1 star of, yeah, that is a delta 2 is a transition function of DFA. So delta 2 star of, you are knowing its start state is Q2. Q2 XA is equals to what? Delta 1 star of Q1 XA. If I am going to prove, then we can come to the end. So let me take this part. Yeah. Now what I have to prove? I am starting with the definition of this DFA. Just now I have shown there is a delta 2 star of Q2X is delta 1 star of Q1X. Now I just want to extend this one. There is a delta 2 star of Q2 XA is equals to, I have to prove what? That is delta 1 star of Q1 XA, how to prove? Delta star of Q1 XA, how to prove? Yeah. Let us consider this left hand side part. You are known, right? What is this left hand side part? There is a delta 2 star of Q2 XA is the left hand side part. So let me take that part. Yeah. Consider this left hand side part. What is it? Delta 2 star of Q2 X. Yeah, this is a left hand side part. So this can be rewritten as what? This is equals to delta. This is a, in the very beginning I have given the definition of this DFA. What I have given? Delta 2 star of QXA is equals to delta 2 star of QX A. That is what I have given the definition for this DFA, right? Yeah, you just recall. Yeah, this is a DFA, right? M2. Here what I have done, delta 2 star of QXA is equals to delta 2 of delta 2 star of this one. Delta 2 star of QXA. Delta 2 star of QXA. Right? So, from this, I can rewrite this part as what? Yeah, this part. Delta 2 of delta 2 star of Q2 XA can be rewritten as what? Delta 2 of delta 2 star of Q2 X Q2X A, that A as it is. Right. So, this can be rewritten as what? This can be rewritten as what? And just now we have concluded, right? That is, you have that equation here itself. Delta 2 star of Q2 delta, yeah, this is what I have proved. Delta 2 star of Q2X is equals to delta 1 star of Q1X, right? If you want to give some name for this equation, let us say C, you can give, it is up to you, right? From C, this part, that is a delta 2 star of Q2X can be rewritten as what? That you write. This is, yeah, delta 2 as it is. Delta 2, just in place of this. Oh, sorry. This one, yeah. In place of this. Just now, right, we have proved the theorem. Delta 2 star of Q2X is what? Delta 1 star of Q1X, and rest of the part as it is. Rest of the part is as it is. And you have one more equation. What is that equation? This is delta 2, right? Delta 2 of QA is equals to. So, this is an important formula I said, right? That is this equation B. Delta 2 star of QA is equals to union of R belongs to Q, delta 1 of RA. Delta 1 of RA. So, from that B, equation B, from that equation B, so, if I let this whole thing as say, if I let this whole thing as say Q, then delta 2 of QA is equals to what? As per that equation B, as per that equation B, just now I have seen, right? First let me write, then later I can refer it back. This is equals to what? Union of R belongs to Q in the sense what? This part, that is delta 1 star of Q1X, delta 1 of RA, delta 1 of RA. This is from equation B. I am just rewriting that cell. See, delta 2 of QA, this formula, that is this. Delta 2 star of QA is this. Union of R belongs to Q, delta 1 of RA. Just using this formula, yeah. R belongs to delta 1 star of QX, delta 1 of RA. Here this delta 1 star of QX, if I, being this X is epsilon here, so delta 1 star of Q epsilon is a Q itself, therefore you have got, that is R belongs to Q. So delta 2 star of QA is equals to union of R belongs to Q, delta 1 of RA. So from this equation, I got this one. I think you are clear. So delta, that one only have got this. Union of R belongs to delta 1 star of Q1X, delta 1 of RA. This can be rewritten as what? This can be rewritten as what? You are known from the standard definition of this NFA. In the very beginning, I have given from NFA. You can just recall that. Yeah, see. This one, delta 1 star of QXA is equals to union of R belongs to delta 1 star of Qx, delta 1 of Ra. So in this form, right, I'm going to rewrite that. So this right hand side part, it is going to get matched. I'm going to replace with that, okay, left hand side part. That's all. Yeah, see, this is right hand side part. So what on the left hand side there you can find delta 1 star of Q1 XA. This is what you have there. So I started the derivation from delta 2 star of Q2 XA. From that I have got what? Delta 1 star of Q1 XA. I think you have understood this. Hence the theorem. So I can say both NFA and DFA, they accept the same language. They both accept the same language. Thank you for watching my video. Wish you a good day.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.